While making the last video, I accidentally broke one of my Arduino boards. It still powers on, but it won't accept my new firmware. Today, I'm going to find out whether I destroyed the hardware or if I can still bring the board back. So, I turned this Raspberry Pi 4 into a portable workstation for hardware and firmware to investigate what actually happened to my Arduino. To figure out why my Arduino stopped accepting firmware, I need a workstation capable of interacting with the board at every layer, from normal firmware uploads all the way down to debug interfaces. Most embedded assessments start with a handful of basic interfaces: serial consoles, debug ports, firmware access, and communication buses. My Raspberry Pi has USB interfaces available from the outside of the case. I can plug my debugger directly into the Pi without a hub, as I would need for my laptop. First, I need enough processing power for firmware analysis. While the Pi has less power than my laptop, what it does have available is more than sufficient for the embedded security work I will be performing. Second, I need this station to be portable. By the nature of the Raspberry Pi being an embedded platform, this requirement is inherently met. Lastly, I want to be able to remote into the Raspberry Pi from my laptop. This will allow me to leave the Pi connected to hardware while controlling it from my desk. Do not judge my password. This device is not facing the internet. Alright, I have teased you enough. A workstation isn't very useful unless it can interact with some actual hardware. I have written this short blinking LED script. If successful, the Arduino's built-in LED should blink once per second. I have written this code on the Raspberry Pi using a standard text editor. First, I need to compile my code using this command. This is a little different to the previous video, as instead of AVRDude, I can use the Arduino command line tools. Let's compile it. Alright, now, using this command, we can first check to see if the Raspberry Pi can see the Arduino and on which port. That way, we can tune our upload to the board. The board I am trying this on is not the same as the bricked board from earlier. This will also help determine if the workstation can perform what I need it to. Confirming that the Pi sees the Arduino, we can now safely upload in peace. During the last video, this board stopped accepting firmware correctly. I want to find out whether I broke the hardware or just the software. Of course, to do this, my workstation needs to access the Arduino's debugging interface. Similar to the last video, I will plug in the hardware debugger and use AVRDude to extract the firmware. First, let's check if everything can communicate. Which it does. Next, I'm going to attempt to extract the firmware from the board and save it as a hex file. If the read fails, there is a good chance the microcontroller itself is damaged. If it succeeds, the problem is probably in software. This success is great news. If I can still read the flash memory, the microcontroller itself is probably still alive. The main question is whether or not the firmware contains useful clues about what went wrong. First, we can convert this hex into assembly, which will be more human readable. I'm going to use a similar tool to AVRDude to convert the raw machine code. Looking at the assembly, this is human readable, but rather difficult to follow. Looking through this, we can see that this firmware is rather short. The board is clearly executing numerous load, store, and jump instructions. It appears to be executable code, but determining exactly what it's doing will require a deeper analysis than we have time for today. Let's check to see if we can read out the bootloader fuse settings while we are here. As we are able to read these fuses, the bootloader itself must be intact. We have been asking quite a bit from our little workstation today. I have opened a new SSH session to see how strenuous our tasks this video have been on the Raspberry Pi. Firmware analysis can be one of the most computationally intensive tasks this workstation will perform. Now let's compile our code and perform our firmware extraction again and see what happens to our CPU. As you can see, my firmware analysis skills are a bigger bottleneck than the Raspberry Pi. My workstation survived the workload. Unfortunately, my Arduino did not. While we may not be able to determine why my Arduino got bricked today, we did build a system that meets all of my requirements. We can remote into a portable hacking station that is fully capable of interfacing with my hardware and its debuggers. I would say this was a success. While this will not replace a full hardware lab, a Raspberry Pi is capable of handling the first stages of an embedded security assessment. Now that I have built this portable workstation, I want to use it to investigate a real device. The workstation works, the Arduino does not. Next time, we are going to find out exactly what I did to this board. See you next time.